What's up, team? Today we are here to talk about solving systems of equations using substitution. Last time we solved the system of equations by graphing. Today we're going to solve a similar system, but this time we're using a totally different method. We're not going to graph a thing today. We're using a method called substitution. So let's say that we had some random equation. I'm just making this up. Say we have like y equals 15x plus 11 or something like that. And you were told that x equals 5. Well, what would you do with that to solve the original equation? You would take that x equals 5 and you would substitute 5 in for x. You get y equals 15 times 5 plus 11. And then we just PEMDAS this thing and we'd end up getting y equals stuff, like whatever it equals, right? We could walk through the process. That's not what I'm here to do today. But we're going to use this idea where you have, x equals something or y equals something, and you're substituting it in. So let's take our attention over here to this example I have for us. System of equations is y equals 2x plus 4 and y equals x plus 5. Our mission, our task here is to find the combination of x and y coordinates that makes both the top equation and the bottom equation true. So where we are right now is we know that y equals this stuff. I'm going to go ahead and underline it in blue. And we also know that y equals this stuff here. I'm going to underline that one in red. So if this y value, we are claiming that these y values are the same y values. This y value equals blue things. This y value equals the red things. So what we can do here is we're going to use the same idea of substitution. It's just going to look a little different. It's going to feel a little awkward. But what we're essentially saying over here is we're going to create an equation that says y equals y. And I think we'd all agree with that statement. But when we plug things in, it's going to feel a little uncomfortable. So this y on the left, I'm going to take the value that's up here in blue. I'm going to say 2x plus 4. So I'm substituting this value in for y. But then for the other y, I'm substituting the red stuff in. So I'm saying that this y is x plus 5. Well, now we have an equation that we can solve for x. There are x's on both sides, so it's a little complicated. I get that. But we just have one variable in this equation. So we're going to solve for x. This is going to give us the x coordinate of our solution. So watch how this works. I'm going to subtract x from both sides. When we do that, 2x's minus 1x is 1x. Plus 4 is still plus 4. And then that x went away, so the right-hand side is just 5. Now, all we need to do is subtract 4 from both sides. And when we do that, we learn that x equals 1. Okay, so we're not quite done yet. This isn't a complete solution. Because remember, our complete solution is going to be a full coordinate pair. It's going to be x comma y. We have the x in the x comma y. So what we're going to do with this now is, essentially, we're doing what we just did over there. We're going to take this x equals 1, and we're going to plug it in to either of these two equations. We get to make a choice. If we played our cards right, we're going to get the same solution both ways. So let's check out. Let's see what that looks like. Let's erase this other example. And I'll take the top equation, which is y equals 2x plus 4. And our claim is that x equals 1. So I'm going to plug that 1 in for x. Y equals 2 times 1 plus 4. Now when we PEMDAS this thing, y equals 2 plus 4, y equals 6. So we are claiming that our solution then is at 1 comma 6. Let's check the other equation too, just to be extra safe. So if we plug in 1 to the red equation, y should also equal 6. So let's check. Y equals x plus 5. So if I plug in y equals, again, x equals 1, so I'm going to replace my 1 with x, my x with 1, and then the plus 5 is still plus 5. 1 plus 5, of course, is 6. So both equations that we plugged 1 in for x, the y value is 6. This means that the solution to our system is 1, 6. This is the combination of x and y that if you plug them into these two equations, they are both true. Now, thinking about our previous lesson where we graphed lines and saw where they crossed, once they were graphed, where the two lines intersected, at that point, if you were to graph these two lines, which we have the skills to do, y-intercept, slope, y-intercept, so we could absolutely do this. If you were to do this and you were extra careful and precise or you used d-isomers or something, I promise you they're going to cross at the point 1, 6. So this is just a different way to do the same thing that we did last time when we solved these by graphing. Okay, stay tuned. I'm going to do one more example here. Okay, we have our two new equations here. Y equals -9 over 4x, and then y equals -7 halves x minus 5. Gross, right? We have these fractions. It's yucky. This one might actually be easier to solve by graphing because these fractions, it's really easy to work with, rise over run, right? We're going to challenge ourselves. We're going to do this one using substitution. So the way that we're going to set this up, we remember that y equals y, so I'm going to set this stuff equal to this stuff. And what we're going to end up with, let's see, I'm going to give myself plenty of space. So I'm going to say -9 over 4x equals, so that's this, the right-hand side of the top equation, equals the right-hand side of this one, which is -7 over 2x minus 5. Our task here is to get x by itself. We've seen problems like this in the past. It takes a little bit of time, but we have the skills to do this. So we want to get just a single x. Right now we have, just a mess with our x's, and there's negatives and fractions and blah. So what I'm going to do is I'm looking at the denominators of both of these fractions. There's 4 and there's 2. There's a common denominator that we can use here. So I'm going to use the number 4 because 4 goes into 4 and 4 also goes into 2. So I'm going to multiply both sides of this equation. So every term on both sides I'm multiplying by 4. And the reason I'm doing this is because it's going to eliminate both of my fractions. So watch how this works here. I'm going to multiply this stuff by 4 and this stuff by 4 as well. So there's going to be some distribution. So on the left-hand side, I'll spell out everything. I'm going to say 4 over 1 times -9 over 4. And then there's still an x here. On the right-hand side, well, we're multiplying everything by 4. So it's going to be 4 over 1 times -7 halves x. So that's the first term that we multiplied by 4. The second term is going to be 4 times 5. I know this looks really complicated and scary. It's about to get really simple. The reason that we chose 4 is because it makes this thing real nice. So let's take it piece by piece. We have 3 different terms. There's this is going to be one term, this is going to be a term, and this is going to be a term as well. So remember, multiply fractions, we go straight across the top, straight across the bottom. 4 times -9, that is -36 over 1 times 4, and then the x is still here. This is going to be a whole number in a minute, so this fraction is about to go away. Equals 4 times -7, that's -28, and then 1 times 2 is 2, x is still there. Again, this is about to be a whole number. Fractions are going to be gone in the next step. Minus 4 times 5, well, that's 20 all day long. Okay, again, I know that this looks gross. This looks way worse than what we started with. I acknowledge that, but watch what happens on this step. If you need your calculators out, that's fine. -36 divided by 4. 4 goes into -36 -9 times. So this fraction here turns into -9, and then x is still x equals. Now this fraction, -28 divided by 2, that's -14. X is still x, and then -20 is still -20. Not messing with that. So all we did in this last step, this is a 14. All we did from here to here is we evaluated these fractions. We just did a little bit of PEMDAS. Now, all whole numbers. There's negatives, and that's, still not great, but we can get there. So the way I'm going to continue this one, I'm going to add 14x to both sides. 14x plus 14x. Adding 14x to this side, negative 9 plus 14 leaves us with a positive 5x's. These 14x's go away. That's why we did that move. And on the right-hand side is negative 20. Oh, nice. Now, all we need to do is divide by 4. That's not true. We're dividing by 5. My mistake. Divide this side by 5, you get x. Divide the other side by 5, you get negative 4. So we've solved. We have learned that the x value that makes both of these equations true is negative 4, if our algebra was correct. So what we're going to do with that is we're going to take this x value, we are going to plug it in to 1, or if you're feeling especially aggressive, you can plug it into both of these equations. And what we're going to do is we'll find our y value by doing that. Let's just plug it into one of these equations, and for simplicity's sake, I think the top one is going to be the easiest. So now over here, I'm going to find our y value. So I'm going to copy down negative 9 over 4x. I just copied that top equation. No math was done yet. Now I'm going to substitute negative 9 over 4. I'm going to substitute our value of x in for x. We're claiming that x is negative 4. And then just because there's a fraction here, I'm going to call it negative 4 over 1. What's PEMDAS? Multiplying fractions. Go straight across the top. Negative 9 times negative 4. Negative times a negative is a positive 36. On the bottom, 4 times 1 is 4. Y equals 36 divided by 4. That is 9er. So our solution to this system of equations, the x-coordinate that we need to plug in is negative 4, and the y-coordinate is positive 9. So your solution is negative 4, 9. Again, if you were to graph these two on Desmos or by hand, if you were very careful, you would see that these two lines intersect each other at the point negative 4, comma 9. This is the way to solve systems of equations using substitution. Sometimes this way will be easier than graphing. Sometimes graphing will be easier than this way. So we're going to practice both ways, be comfortable with both. An example of ones that would be easier to do by graphing, this one, for sure. This is a lot of algebra. This would be easier to graph. The first example we did, much easier to do via substitution. So different tools to do the same sort of job. Okay, let's knock out some practice problems.